Hello and welcome back to Calculus 2. So we are starting our chapter on series. Last time we talked about the sequences. We said that the sequence is an ordered list of numbers. So when you list a sequence, say sequence AN, you will have terms A0, A1, A2, A3, A4, and this is a list, so you are using commas. You can have a formula to generate the sequence. Say AN is equal to n squared minus 1. Now this will generate the sequence when n is 0. You have 0 squared minus 1 is negative 1. Then 1 squared is 1 minus 1 is 0. 2 squared is 4 minus 1 is 3. Then 3 squared is 9, minus 1 is 8, and then you have 15, and then you can go on all the way to infinity. So sequence is ordered list of numbers, and as you can see, ordering is done through this index, through the counter. You're using counting numbers. Even though 0 is not a counting number, we can also add it to the mix. So you can either start your counting at 0, or you can start at 1, or you can start at 17, depending on the application. So sequence is nothing but a list. Sequence is an ordered list of numbers. End of story. You can have the formula, or you can have a recursive formula. Recursive formula is going to use the previous number and then modify it. So I can say that maybe AN plus 1 is equal to 2AN plus, let's say, n. You can come up with any formula you want, right? So now, and then you have to specify the first number. So you can say, let's say A0 is 2. So you either have a world where formula is given, and then you can come up with the sequence, or you have this situation where the formula is given as a recursive formula, which means, guys, you see n plus 1, this means the next term, and AN, that's the current term. So where do we start? Well, as I start writing out this sequence, I have my first term in the sequence. That's A0, right? A0 is always your first term in a sequence. So A0 is given that it's 2. Since that is given to you, now you can use that term to jumpstart calculating the formula. You plug 2 in, right? And then 2 plus 2. Now n is equal to 0, because for A0, you see that n is equal to 0. Yep. So now, what we have those two things, we plug everything in. I have 2 times 2 plus 0 is 4. Now I'm moving to the next term, and the next term is going to use the previous term. In this case, that's 4. N is going to be equal to 1. So this location over here, n is 0. This location is n is 1. The next location, n is 2, and so on. So now I'm going to use the same thing. I use 4 for AN, so that's 8, and n is 1, so 8 plus 1 is 9. To go to the next term, I go 2 times 9 is 18, plus n is 3, so 21. 21 times 2 is 42, plus 4, 46. And you can come up again all the way to infinity. You come up with the sequence. So this is the second way to obtain sequences. So first way to obtain sequences is simply, you have the formula that depends on n, you start n is equal to 0, and you just plow through calculations to how many of these members you want. On the second one, the first one has to be given to you. For Fibonacci sequence, the first two have to be given to you because Fibonacci sequence is a to the n plus of the n plus 2 is a n plus 1. Fibonacci sequence is you add the two numbers and that gives you the next number. So they give you that a0 is equal to a1 is equal to 1. So the sequence is simply 1 and 1. Those are the first two terms that's given to you. And then the next term is you keep adding the last two terms you have. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5.
Oh, we did this.
3 plus 5, yeah, of course you did this in middle school. Is 8 or you? Yeah.
In college.
Of course, but this is the first time you see the Fibonacci sequence. You should be 6. All right. So I hope you have a firm understanding of a sequence. We did all of the other things like bounded, monotonic, increasing, non-increasing, and all of that stuff. And we also said to test sequences for convergence or divergence, we use the limit, right? Test as you send n to infinity, and I asked you guys to review L'Hopital's rule and basics of limits so that you can operate in this chapter, because every problem is taking limits. So now that we understand sequences, we move to the topic of today, and that is series. So series is a sum of a sequence. So you take all of the members from this sequence and you add them up. All right? So you take all of the numbers. So 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 13 and so on. So series is a sum of a sequence. So if your sequence is denoted as an, the sum of the sequence will be denoted with the summation symbol in front, and you will say n starts at 0 and then it goes to certain value on the top. It could be finite value or infinity. We'll talk about that.
Professor Riemann sum, do you remember?
Riemann sum in Calc 1, yeah, but we'll talk about sequence now. Sum now.
Rutgers, the TA, they're grad students. He was like, yeah, I learned in primary school. The Asians, like, yeah, I learned in primary school.
Yeah.
I learned how to multiply and primary.
Move.
To Asia?
Yeah.
To Asia.
That's the answer I can give you.
We're Singaporeans this time of year.
So let's talk about sum.
Bro, can you explain it to me first?
That's what this is for.
Oh, bet.
So sum means addition. And we use the notation which is the Greek letter uppercase sigma. There's a lowercase sigma as well. Looks like this. That's in statistics, right? For standard population deviation, right? Standard population standard deviation. That's what it is. But here we are using the capital letter sigma. So that's the symbol for it, and it just simply stands for addition. So now, if I write summation of, let's say, an from where n starts at 0 and goes to 4, the numbers below and above sum tell you where to start your indexes and where to end them. So this is going to be the first n is 0, plus, because it's sum, a1 plus a2 plus a3 plus a4, and you stop, because top says stop this procedure of adding numbers when you reach that value. So you reach the 4 and then you have to stop. Yes?
I've seen summation with infinity on top.
That we are getting there. So the whole chapter is infinity.
Eager to learn, bro.
I know. Yes.
For the sequence, kind of look at it. When you went from 9 to 21.
I just 2 times 9 is 18 plus 3.
I know, but when you plugged in 4, you added 1, and then when you plugged in 9, you added 3. Like, you never added 2 to anything.
Maybe I missed. I'll have to go back and look.
The next thing.
You add the step that you were at. But let's we'll take a look at it later. We have to focus on this because this really has to be this has to be a big focus now. Okay. So summation is addition. You have the symbol for it, and now you have the basic understanding. Now I can
So to be clear, the number on the top is included, not excluded.
Yes, included. So now I don't have to add terms. This is me adding terms. I can write any formula. I can say summation n starts at 1, ends at 4, and I can have 2n minus 7, right? If I have this, well, now we see that for the first term, I have 2 times 1 minus 7, plus the next term is 2 times 2 minus 7. The next term is 2 times 3 minus 7, and the last term is 2 times 4 minus 7. So you see that we can add all of these values. 2 times 1 is 2, minus 7 is negative 5, plus 2 times 2 is 4, minus 7 is negative 3. 2 times 3 is 6, minus 7 is negative 1. And 2 times 4 is 8, minus 7 is plus 1. So the total is negative 8. So this is the way to compute sums. You write out all of the terms and you add them. There is also a notation for multiplication. If you put pi and you go n from 1 to 3 of n, that's just 1 times 2 times 3. So for multiplication, you use pi. For sum, you use, it's not a part of our, I just wanted to put it out there because as you research this online, you might run into it. So you know what it is. So summation is addition and pi would be multiplication. They work exactly the same way with formulas. So now, some of the properties of sum. For instance, you have a summation of c times an, where n starts at, let's say, 1 and goes to 9, whatever. When you have constant multiplying, you can kick the constant outside, go summation, n goes from 1 to 9 an. So you are allowed to kick the constants outside. Why? Well, because it's addition. So you get to factor things. If I had some large number, some number over here, let's say I had a number 3 in front. Well, that 3 would be repeated everywhere, and you see that you can factor that 3 out, right? So we are allowed to kick the constants outside of the integral. So constant jumps out. That's one of the rules. Summations can be split anywhere. We're going to use this rule in this particular lecture when we actually start doing these things. This is just preliminary knowledge that you need to have to survive. So let's say you have a summation when n starts at 0 or 7 or whatever, and it goes to, let's say, 10 of some formula. You can split this anywhere. So you can have a summation where n starts at 0 and goes to 6 of an, plus summation n starts at 7, thank you, and then goes to 10 to end the whole thing. Because 6 is inclusive, that was your question before, 6 was inclusive, therefore 6 belongs to this term, you have to start with 7. Now, this is discrete mathematics, therefore there is no 6.1, 6.5, 6. Any of that stuff, so continuity doesn't exist there. It's just a value 6, and the next one is 7, and the next one is 8, and the next one is 9. So if you go up to and including 6 in the first, then you start the next one from 7, and you go from there. So you are allowed to kick constants, and you are allowed to break these apart into multiple sums. Now, you can add sums and subtract sums. Multiplication of sums is a living nightmare, and division of sums, don't even think about it, right? So if I have two sums, summation where n starts at 1 and goes through to 6, an, plus the second summation has to start and end with the same value. So n equals to 1 to 6, bn, then I can have a total summation of an plus bn, and then n goes from 1 to 6. Now, what happens if they don't start at the same number? Well, you have to peel off some terms, make them start at the same number, and then add them. So, if any of the values on the bottom or on the top are different, you cannot add those series. So, if I have a series that starts at 0 and goes to 6, an, and I need to add to that a series that starts at 1 and adds at 7, bn. I can't add this because they don't start at the same counter and they don't end at the same counter. Now you will say, well, 6 minus 0 is 6 terms and 7 minus 1 is 6 terms. Yeah, it's not the number of terms. They have to start at the same n value because it's the n value that plugs in into a and b. But for the first term, on the first one you plug in n equals 0, on the second one you plug in n equals 1, and if you are to combine these two into a single one, which one wins, 0 or 1, right? So you can't do it. However, you can peel off the terms that are making it uneven and then just add what's even, and then add manually the stuff that you peeled off. What do I mean peeled off? Well, I see that the bottom counter should start at, on the first one at 0, the other one at 1. What's common for both? Well, 1 is common for both. So what I'm going to do is I'm going to actually kick out a0 plus, and now I have summation that starts at 1 and goes to 6 for an. Then you go plus summation, n starts at 1, right, for bn, but then you realize that it goes to 7. That's more than 6. So you know what? I'm going to actually go and end at 6 and say plus b7 as a term on the outside. So now look what I have. I have a0 plus b7, and then I can combine the two series as n goes through 1 to 6 of an plus bn. So now I can combine them because I peeled off the terms that were making them uneven. Stuff like this for chapter 3 in differential equations, extremely important. There they are laughing in the back. Because when this is not presented very well in a class, when you are in Calc 2 or Calc 1, depending on how well your Riemann sums were done, this is insanity in DFQ. So these types of things, like peeling terms off, making sure that counters start at the same spot, and all of that stuff, will be just a simple, quick step that you have to brush off to get through derivatives of these things to plug them into, first and second order differential equations to solve them. So this stuff is extremely important, and it's coming back, right, big time. So these are your basics of series, of summation notation. There is a lot more to it, obviously. There are courses upon courses on this. But we are now focusing only on these basic ideas. So we start with summation notation with the Greek letter sigma, capital sigma. and then we understand that we have the number below, number above, and those are the counters, where the counter starts, where the counter ends, and then whether you have AN to change indexes, or you have, you can also have this in the exponent, right? So you can have summation, n starts at 0 and goes through, let's say, 3 for n, not n, let's say you have x to the n, right? Now this is already a power series. This is chapter 9, but you see that your counter n, right, is still present. Now you have the variable. We never had variable before. It was only counter n and numbers. Now I tossed in an x, so this is the first power series that you guys see. And this is all you see in chapter 9. So what is this equal to? Well, it's going to be equal to x to the 0, right, because first n is 0, plus x to the 1, plus x squared, plus x cubed. So this x to the 0 is 1, so this is 1 plus x squared plus x cubed. And look what you got. You got the polynomial. The power series will be giving you polynomials in chapter 9. It will be a very nice condensed way to write infinitely long polynomials, right? Now this is where, Sharif, your question was, I've seen these things with infinity in it. Sure, you've seen these things with infinity in it because our series, which is our summations, they could be finite if you put a finite number on top, and they could be infinite if you put infinity. So when I write a sequence, right, let's say I write the sequence 2n. So sequence 2n. Sorry, an equals 2n. I give you the formula. You know that this sequence will be given as the first n you are taking at 0 is 0. 0 times 2 is 0. So 0, 2, 4, 6, 8, 10. This is your sequence of even numbers. Now, series would be summation. Let's say n starts at 0 and goes through 4 of 2n. And now this would be, we don't use the set notation anymore because it's not a list. Now it's addition of numbers. So we just go, okay, the first number, 0 plus 2 plus 4 plus 6 plus 8. And then it ends, right? We have 5 terms because you have 4 numbers and 0, right? So it's 5 terms. And you can compute this. It's equal to 20. So you see the difference between sequences and series. The only thing they have in common is they both start with an S. That's it. Right? One is the list of numbers. The other one is addition of that list. And it gets you a number at the end. Now, series, here in blood, series can be infinite. Can be infinite, which means summation when n starts at 0 and goes to infinity of some formula that you plug in there, whatever formula you have. So infinite series is a series where you have infinity, and that's the only one we focus at, because I don't care about finite series. They're not interesting. They're not fun. They always converge, because whether you have 4, 5 terms or you have 5,000 terms, you can always add them. Depending on your time, you might want to punch those 5,000 terms one by one in your calculator, right, if you have the time. If you don't have the time, you sit down and write a script, right, that will add those numbers for you as a computer science, right? But you don't have to be computer science for that. It's just something that you should be able to write in 3 lines right now, no matter what your major is, because we live in a world. Infinite series are the ones that are interesting, because those could add to a finite number, and we call that convergent, or they can add to infinity, and we call that divergent. So we only consider infinite series because finite series are not interesting. They always converge.
I like that.
So here we go.
Why can't they all just converge? I like it easy.
So finite, exactly. But you also will get nothing done. So all of the technology is run by infinite series. So finite series always converge. And that's the end of the sentence, and that's the end of us talking about finite series.
Hey.
Infinite series.
It was good while it lasted.
So infinite series.
Never.
Either.
Not either wrong, bro. E. That's not.
Either converge or diverge. So infinite series are the ones that we will be considering at all times. And we are going to learn 10 tests. You are going to memorize 10 different tests, their names, conditions, and outcomes to test different types of infinite series. Now you're going to say, hold on. I said, no, you memorized multiplication tables before. You memorized different types of derivatives you have to use for different types of functions. Product rule, quotient rule, chain rule, implicit differentiation, logarithmic differentiation. You take a look at the problem and you know which differentiation technique to use. In chapter 7, you just had your exam on all different types of integration techniques you had to memorize to take a look. Is it a U sub? Is it a trig sub? Is it by parts? Is it partial fraction? Right? You look at the integral and the function and you know which one to use. Now the same thing is going to happen for your series. Depending on what the formula inside the series look like, you are going to use telescoping series or the root test or the integral test or the P series. There will be 10 of those. So now we, for the rest of this chapter, chapter 8, we have sections 3, 4, 5, and 6. So these 4 sections are covering those 10 different methods to test series for convergence or divergence. Now, it's not immediately apparent why we want convergence and divergence and these kind of things, because we can't teach everything at once. So let me give you a quick preview why you want to learn all of this. Well, why you need to, whether you want it, that's yours. So you start first with the understanding that the world around us is governed by mathematical functions, whether we want it or not. We are able, through science and measurement, to figure out what the mathematical models are for gravity, for force, for interaction between objects, for motion, you name it, we have it, right? Except theory of everything. Now, those things are modeled by functions, and the functions cannot necessarily be integrated. They cannot necessarily work in certain environments and so on. So what you do is you approximate those guys with power series, which is our chapter 9. Now, when you have a power series, you want to make sure that the power series converges to the function that was approximating. Otherwise, your calculations are garbage. I mean, the numbers that you're going to get will be garbage. So there's your convergence right there. So you first have to learn the simplest possible creature, which are the series. Then you learn power series and their relation to functions. And then that convergence kicks in, and we talk about radius of convergence and interval of convergence and all of these things that are actually used in your coursework later on. You want to take any kind of serious engineering course, not introductory ones, that you have in your first 2 years or 3 years of undergrad work. But the serious stuff, 300 level, 400, 500, 600 level courses, it's power series and convergence everywhere. So, and it starts with partial differential equations and thermodynamics and all these kind of things, right, for you mechanical engineers and electrical engineers with the signal analysis and everything else. It's just power series everywhere. So we want to learn the easiest, cheapest thing first, which will have pretty much zero application. It is going to be as boring as learning algebra, because you could put, you know, maybe 10 applications on your fingers, right? Count 10 applications that you could use algebra for as you leave the classroom. And for most people, and I'll sign it off too, I don't care, right? Algebra is boring. It's boring, it's dull. You memorize the rules, and then you just plow through it so that you can finally get into pre-calculus, learn about the function, and then have some experience with exponential functions, logarithmic functions, and then have the fun with actually application and usefulness of the whole subject, right? So now, what you are doing with chapter 8 is going to be the same thing. That's that boring part that you have to learn so that the more interesting, useful things can be built on it. And that's chapter 9 already.
Hey.
So what I'm saying is persist, power through, and try not to resist the material from the point of, I will never use this crap, I don't need this, I don't see how it's used, why do I have to learn it? I just told you, it's going to be boring, you're not going to use it for anything in particular.
Except the exam.
It's just mathematical gymnastics and exam, exactly.
The exam is very important.
But then, chapter 9 will open that thing for you, just like pre-calculus opened up algebra to the world. All right?
You mean algebra
so just be
open pre-calculus to the world?
Well, no, algebra makes pre-calculus possible, but the pre-calculus is the one that actually is useful. And then on shoulders of pre-calculus, you have calculus. So you go through the boring part first to learn those basics that you have to know.
Definitely.
And then you
funnest math class I've ever been in.
and then you move on to better and bigger things. All right, guys. It is time for us to take a look at the meaning of the convergence. All right? So, convergence. We define the convergence as the finite limit of partial sums. So, convergence is a finite limit of partial sums, meaning partial sums will create a sequence of partial sums, and then if that sequence converges, your series converges. So let me give you an example of this to make sense of the whole thing. So say I start with summation that n starts at, let's say, 1 and goes to infinity. It's infinite series. And I just have n here, simple n. So what is this series? Series is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus ... going forever. So you are able to write out this series. Now you cannot write all of the terms and you cannot add them all because it goes to infinity. Now, what you can do is you can find partial sums. So your S1 is going to be just 1, right? One term. Your S2 is 1 plus 2, and that's 3. Your S3 is 1 plus 2 plus 3, which is 6. So partial sums are just picking 1 term, 2 terms, add 3, add 4, add 5, add 6. So that's what the partial sums do. So now we have our S4. S4 is 1 plus 2 plus 3 plus 4, which is 10. S5 is 1 plus 2 plus 3 plus 4 plus 5, which is 15. And I'll just put 3 dots here because this will go to infinity. What you have from here is you have a sequence 1, 3, 6, 10, 15, and it's going to go forever. Now these numbers are known as triangular numbers, and there are, things that you can do with this. The interesting thing over here is that when you look at this sequence, you see that this sequence diverges. So over here, I will say this is a divergent sequence. Right? It's a divergent sequence. Now, this means that the summation of n will diverge. That's what, right? So when you are looking at this this concept, well, I can put 1 to infinity here. Because the sequence of partial sums diverged, the summation of the series will diverge. Now, it doesn't take too much brain power, and even if you use intuition, you won't be wrong in this case. As you keep adding these numbers to infinity, they have to add to infinity because it's constantly increasing, right? But then you can consider another example, which is, let's say you have, let's use 1/2 to the n, 1 over 2 to the n. 1 over 2 to the n, and let's have n start at 0 and go to infinity. What are your terms here? Well, the first term is 1 divided by 2 to the 0. 2 to the 0 is 1, so first term is 1. Plus 1/2 plus 1/4 plus 1 over 8 plus 1 over 16 plus 1 over 32 plus, and that thing is going to go on forever. Now, what you do is you create your partial sums. Partial sum 1 is just 1. S2 is going to be 3/2. And then S3 is going to be times 4, so that's 4, 6, 7 quarters. And then S4 is going to be, so we have 7 quarters plus 1 over 8, that's 14, 15 eighths. 15 eighths. S5, so we have now 15 eighths plus 1 over 16, so double this one, 31 over 16, and so on. This will go, as we said before, this will go forever. This thing creates a sequence of partial sums: 1, 3/2, 7 quarters, 15 over 8, 31 over 16, which is a convergent sequence, and that will imply that the summation of 1 over 2 to the n, as n starts at 0 and goes to infinity, converges. So technically, this is that painful way to solve any problem. Now, the hard part is actually to come up with what kind of sequence you actually get here to do the limit, to do the convergence. I didn't do that. I just told you what the answer is. Because this is not the way to solve the problems. This is the way to define what's happening. To solve convergence and divergence problems of series, you will have to memorize 10 tests so that you don't have to go through the horror of calculating partial sums for the sequence and then figuring out which equation satisfies that so that you can take the limit of that and then see, right? So instead of doing all of that stuff, we have 10 different methods. You know what this is equivalent to? For integration, your Riemann sums, and for your derivatives, doing the f of x plus h minus f of x. You remember that? Yeah. So, you have the definition way to compute this. So you can technically scrap the rest of the chapter and say, anytime I see infinite series, I'm going to spend eternity to figure out whether it converges or diverges this way, which is possible, but it's highly impractical. So instead of that, you do what you always did in the past. Instead of adding 8, 6 times, you memorize that 8 times 6 is 48, because you want that shortcut. You don't want to go 8 plus 8 is 16, plus 8 is 24, plus 8 is 32, plus 8 is 40, plus 8 is 48, right? There is my 6 8s. Instead, you opted out. Well, actually, someone opted out for you. They told you have to memorize it, right? You memorize that 6 times 8 is 48, and you don't have to add term by term. So now, we are opening the chapter up. These 4 sections cover 10 different techniques and tests to figure out convergence and divergence of series, so we don't have to go through partial sums and the original definition for convergence or divergence of series. So the first one that we are discussing in this chapter and section is going to be geometric series. Since this is not the honors option of the course, and you guys are not mathematicians but engineers who just have to loosely use this stuff, I will not go through derivation of these things. I will be telling you exactly what is the formula that you have to memorize to survive the thing. So this is what you're memorizing. You're memorizing this. Summation n starts at 0, goes to infinity, a r to the n, right? That's the form. And then we'll say, over here, converges if r is in between, -1 and 1, and diverges otherwise. Off of the convergence thing, we also say that summation is equal to a over 1 minus r. So, please use common sense in this case. If there is convergence, it adds to a finite number. So, if it converges, it has a sum. If it diverges, well, common sense, it added to infinity, so there's nothing for you to compute there. Example. Guys, this is what you are memorizing. This is your formula. This is what you will be using. And if you don't know this, you'll see exactly what's going to happen in 2 seconds. Here's the example. Summation of n going from 0 to infinity of 3 times 1/4 to the n. That's the problem. We are asking convergent or divergent. This is the statement for the problem, for every problem for the rest of the chapter, okay, chapter 8. The question is, does the series converge or diverge? So all of the problems have the same question. 50-50 chance of guessing. Good. I will show you how quickly that diminishes, actually. If you think that you are going to get the exam, if I am to put the exam with 50-50 chance, first of all, 50% chance, 50% guess, 50% grade, it's not passing grade. Second, it actually is going to be much less than 50%. Because if you are doing the random guesses on 10 questions,
Yeah, we're just gonna write divergence.
You just write one for every problem. How stupid are you to
Yeah, how stupid would you be to learn the concept, right? You just write the same answer. You just write the same answer for each one, and obviously you have to guess it, right? See, the issue that immediately offsets that is the same, the one that makes casinos money when you play roulette. You know the green one on the roulette? That's the one that tips the odds to the favor of the house. So you can walk in and you can win $10,000. For them, that's nothing, because casino is open 24/7, and people will be losing 24/7 because of the green field. And you walking in once and winning 10K, they don't even feel it. They don't even 100K. Doesn't matter. It's irrelevant the amount of money you win, because they're open 24/7 and they're winning all the time because of the green field. So now, for 9 out of 10 tests, you are going to have convergence divergence. That's like black and red, right? When we go to an 8.6 alternating series, they're going to have divergence, convergence absolutely, and conditional convergence. There's a green field. So the house has to win. If you're going to guess, the house will win 100% of the time, right? On average, if everyone comes in and guess with those odds, right, I should be winning at about 45%. I mean, winning at 55%, and you should be losing at 45%. So the house always wins. You have to understand that. All right, guys. So now that we discussed that you actually have to learn this stuff, going back to the example, let's see how difficult it is to use series. Ready? You use your eyes and you look at the problem and you determine that R is equal to 1/4. Do we all have mental capacity to do that? You realize that 1/4 is between a -1 and 1, therefore problem is convergent. Done. This is it. So to figure out convergence or divergence for geometric series, you just look at it. Now, what's going to happen if you didn't memorize the outcome? If you do not memorize this over here, can you do the problem? The answer is hell no. You can guess, and maybe guess it right, but the trick is that if you do not memorize the formula, you don't get to do the problem. And you see that it's an absolute joke to do the problem. You look at the problem, you realize that your R is 1/4, and you know that 1/4 sits in between a -1 and 1, which means convergence by geometric series, which is the definition above. This is why I said, do not play with fire. This chapter, entire chapter, could be the biggest joke you ever did or the worst nightmare you've ever seen. There is no in between. You either memorize everything and you solve the problem like this, or you just say, you'll see if you can BS anything on the exam. And right, I didn't memorize these things. I made a mistake as a student. I went in and I said, I'm going to reason with this because, obviously, this should look this way and this should look that way. It was terrible, right? So, day 1 today for your series, test 1 out of 10. There you go. You have the problem, you have the conditions. If you memorize the conditions, it takes about 3.5 seconds to do the problem. Next, what is the sum? So if it converges, you can calculate the sum. Well, your A is 3, 1 minus 1/4, just plug in a formula which you memorized, and you compute. So this is 3 divided by 3/4, which is 4, exactly. And this is now that awesome, awesome, awesome part of mathematics, where you go and you say, I just added infinitely many numbers, and I got 4. Right? The funniest thing that my friend Brian ever did is when the school asked him for $10 because he didn't pay for application for graduation. He earned his degree and he was ready to transfer and everything was set. School wouldn't issue him diploma because he didn't pay $10. He came up with a series and wrote that on a check, and in a memo line said thanks for the knowledge, and gave that check in. The series was actually adding up to 10. So they actually cashed it. The school cashed that check with a series written on the line. You know when you have them check to write in amount, right? But you would put 10.00 with a little line so people can't add extra after that. That's the purpose of the line when you're writing the check, right? If you write 10, I don't even know if you know what the check is. But in a box when they put this line on the side, that's because if there is no line and there is space there, you make this into a comma, you add another 0, and then you add your 2 zeros, and the check that was on on $10 becomes the check on $10,000, right?
Nick, let me get a check, bro. $10.
No, when I write the check, I write 10,000, right, in a line like this.
All right, then I just added.
In writing, you just add 1,000. Yeah, you add one word.
You got the little cents there. They get it right over the cents.
You gotta do 1 over.
And then you have to write out.
Yeah.
You have to write out.
Yeah, I know. So guys,
Stop playing with me, Nick.
this is what the geometric series look like.
They teaching me how to do bank fraud.
No, I'm just telling you why people put the little line.
Yeah, nah.
So you can't. So you can't do it. Plus, people don't use checks anymore. So
Yeah, I mean, you can't like defraud
You can just send them
print it out check.
yeah.
You still gotta pay, like,
All I need is your signature, bro. Look at your signature and memorize it. Nick.
Next problem.
And I think.
Summations, no C. Okay. Next one, guys. Summation starts at 0, goes to infinity. The problem is 2 times 6 to the n. So, what is the verdict? Diverges, right? You memorized that if r, in our case r is 6, if r is not in between a -1 and 1, it diverges. So guys, the problem is solved. I put the line through and we move on. You memorize what I have in a box. Example 1, r was a quarter, fits here, converges. In a second example, r is 6, fits there, diverges, done. We go to the next type. Now, before we move to the next type, there is an issue that we have to deal with. And that issue is you have to be very careful when you are learning these that all of the appropriate numbers and letters and variables and parameters are the way they are in the definition. Primarily for geometric series, this puppy here, which says n is equal to 0. So what happens on the exams and what happens in differential equations, that thing jumps to 1 or 2 or 3, creating the disturbance in a force. And that's this one over here. That's where the disturbance happens. So let's take a look at summation. N starts at, let's start n at 2 to infinity. For 3 times, let's go with 1/5 to the n. So this is a problem.
You have to like peel it off.
Well, you can't peel off because you are actually way beyond, right? Peeling off would make it a 3 and then a 4 and then 5 and make it worse. You can't peel off. And you can't stuff anything back in.
Sounds great.
So what I'm going to teach now is something that it's called shifting the counter. And that is going to be crucial for your chapter 3 differential equations later on. So it shows over here as a meaningless exercise, not a meaningless because that's the way to solve the problem, a pointless exercise. There you go. There is no application assigned to it other than mathematical gymnastics. However, In power series for differential equations, you have to do it so you can combine the terms. So we start solving this problem. We immediately say r is equal to 1/5. Yay. That's less than 1. Implies convergence. And we're happy campers. We're done with the problem, right? But then as soon as the question is, okay, it's convergence, what's the sum? This is where issues become here in blood. Cannot answer until n equals to 0. Because in the definition, the one that you are memorizing, the formula that is given to you is valid only if n is 0. In your problem, n is 2. So the formula you have doesn't apply until you fix that problem. So now we are learning shifting the counter to actually push this back to n equals to 0. We need to shift the counter back to 0 so we can use s equals a over 1 minus r. What's going to happen when I shift the counter, you will see that your a is no longer 3. Your a will be a different value. It will be 3 over 25. So we have to learn how to shift the counter. Here, shift the counter underlined. That's what we are doing. So the way we do this is we start with n equals to 2 to infinity of 3 1/5 to the n. And we say, I need a 0 over here. If I need a 0 over here, I'm going to subtract 2 on both sides of this equation, n equals to 2. When I do that, I get on the left-hand side, n minus 2 is equal to 0. And now I'm going to assign a variable, say k, to this n minus 2. So substitution that I am using is k equals n minus 2. So this is the first part of the work, which depends what you're subtracting here, depends whether the n is 1 or 3 or 17, right? That's the number that you will be subtracting. That determines the formula you're using, that determines the substitution you will be using. So now, when I started doing this, what I have is now summation. Obviously, infinity will stay on top. 3 and then 1/5 to the n. Not to the n, sorry, just 1/5. Now, this part over here in black, this part will become k equals to 0. You don't get to change this to k without changing that to k. You better know that by now, because you had u sub, you had the trig sub, you had the 5,000 different versions of sub of some kind somewhere. You don't get to change some and not change others, right? Be nice, don't discriminate. Otherwise you're terrible people. So what you do is, if you switch that n into k, you have to switch the other n into k as well. Now, that's very easy to do, right? You go here, you say, what's n equal to, and n is clearly k plus 2. So this becomes k plus 2 as the exponent. Now, please don't celebrate prematurely here, because yes, you did fix your k to now counter to go to 0, but you messed up your exponent. This over here doesn't say n plus 2 for this formula to work, right? So you fixed on one end, and then you messed it up on the other, right? Now, luckily, what you can do here is you can peel off the plus 2, right? You can peel the plus 2 because maybe you know, maybe you don't know, right, in algebra, the formula says that x to the n m times x to the n is x to the m plus n, right? So that's what I have. So I can split this now. I can split this now into summation k goes to 0 to infinity 3, and then I have 1/5 to the k times 1/5 squared. I'm using the basic algebra formula from elementary algebra, algebra 1. I'm using that formula to split that k plus 2 into 1/5 k, 1/5 squared. And when I do that, now 1/5 squared is 1 over 25. And as I promised, right, at the beginning of the problem, you are going to have 3 over 25 to be your a, and then 1/5 to the k stays there. So now, if you use the sum equation, your a is 3 over 25 divided by 1 minus r, and that r is 1/5.
Oh, shit.
And you get your answer.
That's a no.
Oh, shit. He could get $2. Oh.
I know, right? It's amazing. So this is mathematical gymnastics that you are doing here, guys, just for fun. Unfortunately, I don't have my differential equations notes to show you when this is done on expressions of power series. But that stuff is the same. It's the same. And Matt and Kevin in the back, they will vouch because they did sit in a DFQ and they both beasted through that like nothing. So yeah. So now what I'm going to do is I'm going to multiply top and bottom by 25 to get rid of the double fraction. So times 25 and times 25 to compute this. So this becomes 3 divided by 25 minus 5, which is 3 over 20. So now we
and circle it. You gotta write that converges. Come on, bro.
Yeah, converges to 3 over 20. So this is our answer, and we say converges to 3 over 20. Now, what was the problem? The problem simply asked, is this convergent or divergent? And if it's convergent, what is the sum? You just look at R, and you immediately know convergence and divergence because you memorized the formula up there. So you're done, right? Then you move to the next one, and you realize that it starts at 2, which is triggering all of the green stuff. And then you can finally, when you shift the counter and you get your exponent back into the basic form, when the problem matches the formula, 0, A, R, and then exponent without anything to it. Only when that matches the original formula from the definition, you are allowed to unleash the sum equation and you can come up with the answer. Yes?
For geometric, if it's in like the format, I guess, it looks like a geometric, whatever the other ones, can we always just do R to the whatever the n value is? And like multiply, like we just,
yes.
Okay.
The answer is yes. But then if you memorize it that way, and then when the shifting on the counter comes in, when the derivatives are around and you don't know the procedure.
Is that for Calculus?
No, that's for DFQ. This is the part where I tap your shoulder and I say, welcome to.
But is that Calculus though?
No.
Oh, well then
Welcome to Output.
Oh, you'll deal with that when you get there, right?
Well, no, there is no Calculus after this.
There is.
Hey.
Well, not for me.
Knowledge is power.
You'll just take it to see next
Tell him.
Wait till next summer. We'll see next.
Yeah, we're coming next summer.
I'm gonna take Calculus. I'm gonna come back. I'm doing it.
All I need to do is to not see you for like 5-6 years, and there you come back. I actually need that differential equation, right?
I mean, if I do, then I maybe. But as of right now, I mean, looking at my requirement, I don't think I need it.
I think it's some nick him up. I gotta see you next week.
Guys, we are done with geometric series.
Done.
We are done with the geometric series. We have one more in this section. And that one is called telescoping series. The book doesn't actually recognize that as because this book is not the greatest. It doesn't recognize it as a method, but it is a method. They only give you one example in a text, and then they give you maybe 4 examples in the homework. So it's not really well represented. But on the list of 10, it's one of the 10 methods. So we need to learn telescoping series.
What the hell was that noise, dude?
I don't know. I don't like methods that I can't spell. Telescoping. Slow, bro.
All right. So, guys, this is
95.
This is the one where we get to do limits. We also get to do some stuff. But first of all, the form. Summation of, let's say, bn plus k minus bn when n starts at any value, can start 0 to infinity. So that's the form. That's the form for the telescoping series. And the telescoping series doesn't trigger a formula and like you memorize conditions and things like in geometric series. It triggers a procedure that you get to do. So over here I'll say procedure will determine convergence or divergence. So you have to learn the procedure in this case. So I'm immediately going to teach the procedure because that's it on the example. Here's the example. Summation of 1 over n plus 1 minus 1 over n. And we can start, let's say, at 2 to infinity. It doesn't matter where you start. So I'll put arrow here and say, does not matter where we start. Okay, so now we have this. What is the procedure? The procedure is to write out finite number of terms and then take the tail end that we are not writing out and use it in a limit. If the limit ends up being finite, you had a finite series plus a finite limit is a finite number, therefore convergence. Or you have a finite number plus the infinite number, which is infinity, which is divergence. So, mentally is a very simple idea. Remember how I said you take the series and you cut it into 2 series. Now, the way you're going to cut this is you are going to cut it into a finite portion plus the infinite portion. And you are going to use limit on the infinite portion, and you are going to use just a simple addition on the finite portion, and that, when you add the 2, you either get convergence or divergence because you either get a number or you get infinity, right? Those are the options. So now, if I want to write this out, I'm going to say this is going to be summation from n goes from 2 to k plus summation n starts at k plus 1 to infinity, right? So this is what I am doing. I'm splitting now you see I'm using k as a finite value. I didn't pick 10 or 100. I picked a general finite number k. So that's what I did. Now, what I'm going to do is I'm going to write this out, and I'm going to limit this as k goes to infinity. So those are the 2 things that I'm doing. Let's go. I'm going to write out a whole bunch of terms over here. We start at 2. So I have 1/3 minus 1/2 plus 1/4 minus 1/3 plus 1/5 minus 1/4. Where am I getting these? Well, I'm getting these. The first one is n equals to 2, because that's the first number I'm using, n equals 2. So the first parenthesis is when I use n equals to 2, so that's 1/3 minus 1/2. The second parenthesis that I have over here is n equals to 3. Well, great. Yeah, it's 4 and a 3. So as I go like this, I can go as high as I want, right? But then eventually we get bored. So what I'm going to do now is I'm going to go and look at few terms in the back. So what are the terms in the back now? Well, in the back, I'm going to start reaching those k's. So the last k term that I get to write is exactly the same as the problem. So let's put a setup for a few of these. There we go. The last one over here is the first one you write, is 1 over k plus 1 minus 1 over k. Because the last one looks always the same as your original problem, right? Because the last number you're plugging in for n is k, right? You see it up there. It's k. So now, to go the term before, all you need to do is to subtract 1, right? Because this goes down by 1 and this goes down by 1. So what do I have? Well, over here I have 1 over k minus 1 over k minus 1. Subtract 1 again. 1 over k minus 1 minus 1 over k minus 2. Subtract 1 again. 1 over k minus 2 minus 1 over k minus 3. So to get these things, right, to get these things, you plug in the k for the last term that you are computing in your terms of the finite terms, and then keep subtracting, because this is the term before, well, it goes minus 1 on each k. So if this was k plus 1 minus 1 is k, and k becomes k minus 1. Then k minus 1 becomes k minus 2, k becomes k minus 1. You can write out 30 terms if you want to, because if you start at the last term and you keep subtracting 1, 1, 1, 1, you keep subtracting these terms throughout, you will go back all the way to how far you want to go. Where is the genius of the method? Canceling.
Oh.
Look at this.
Plus 1.
You have positive 1/3 and negative 1/3. Gone.
Oh.
You have 1/4 and negative 1/4. Gone. You have 1/5 and negative 1/5. Gone. Do you see that this procedure will actually kill all of these over here as well? If you go back and cancel from the back, you get the same thing. Positive 1 over k, negative 1 over k, gone. K minus 1, k minus 1, gone. K minus 2, k minus 2, gone. K minus 3 will cancel. K minus 3 right there.
Yes, why keep going?
I know, right? This is where we get excited. So now, guys, what do we have? What we have left is the only thing that survives in the front, which is negative 1/2. And remember that I need to take the limit of the last term. So plus the limit of 1 over k plus 1, and we shoot that k to infinity. Now that goes to 0, because you're dividing 1 by infinity for a total of negative 1/2. This series adds to negative 1/2. We just added infinitely many numbers and we got negative 1/2. Next time, yeah, thank you. Guys, next time someone tells you, what do you know? You can add infinitely many terms, right? You can add infinitely many terms in 2 minutes. Challenge them to even count to infinity. It's not that you just counted, you also added and gave the answer. I don't think they would even be able to count, right?
If you could count to infinity,
You'd be Chuck Norris. But you can't, so. So guys, this is the procedure for telescoping series. It's completely new, out-of-the-box type of thinking that you have not used before. This is not solving equations. This is not taking derivatives. You can see how different this is than anything you ever done before. This is why it's so dangerous, right? So what you are supposed to do with this is practice it until you start bleeding under your fingernails, because it's new and different. Yes?
So will it always or most likely come out to be that it's like the second term of the first one, and then we'll get the first term?
The answer to your question is hell no.
hell no.
It's not no, it's hell no. So let's take a look at the problem where we have
More things that are left after that.
exactly.
What?
Oh, secret test. Crazy. I mean, the videos after like 2 minutes. Can't follow.
Dude, great. No, I fucking love these songs.
Great. Yo, he's a nerd, so like he owes $1 million.
I'm a nerd, but I'm also a nerd.
Summation of n starts at, let's say,
What did you say this number?
you had enough, right? Overload, right? You're done. Let's go 3 to infinity. Let's go with a 3 to infinity. Let's go with, say,
We get nervous.
1 over n plus 3 minus 1 over n plus 1.
Bro, good luck. The exam's tomorrow, though. You wait.
So this is our new problem. The first thing you go, guys, you see. All right, you see this is a series problem, right? It's series, and then so far you know 2 tests. Immediately you're going to ask yourself, is this geometric series? Because geometric series is solved in 3 seconds. And you say, no, it's not geometric series because it doesn't fit the form of geometric series. Well, the next series test you learn is telescoping series. So, ta-da, it's telescoping.
Is there one formula that covers like all of them?
No,
It's
that's why I said procedure. Otherwise it would be in a box, like geometric, right?
Like if there was one like generic formula, but it takes forever to solve out, but
No,
it would work.
nope.
That'd be too easy.
This is a procedure. You are going to get formulas for everything else, right? Theorems and formulas for everything else. This is a procedure. All right, so you are either paying attention or you're not. I'm just going to finish this and whatever you guys. So here we go. I'm going to set up a few of these. I'm going to set up 6 initially. And then I'm going to do 3 dots, and I'm going to set another 6. So we might need more, but let's start with 12, right? 6 plus 6, and then we'll figure out. All right, so here we go. What do I have? Well, n starts at 3. If n starts at 3, that means that the first calculation is n equals to 3, and the next calculation is n is 4, and the next one is n is 5, and then n is 6, and then n is 7, and then n is 8. Because series are some of the sequences, and sequence is the list of ordered numbers, and ordering is done through counting 1, 2, 3, 4, 5, 6, 7. So if you're starting at 3, you have to pick up at 3 and go 4, 5, 6, 7 without skipping a beat. So on the back end, the last one is n equals to k, and then n equals to k minus 1, and then n equals to k minus 2, and so on. Okay, let's compute this. So n equals to 3. I hope you all see that's 1 over 6 minus 1 over 4. Bueno?
Yeah. Bueno.
Next one, n equals to 4. That's 1 over 7 minus 1 over 5, right?
Bueno.
Now I'm going to ask you, what cancels between these two parentheses? And you say nothing, right? Then the next one, n equals to 5. We have 1 over 8. Still no cancellations. Minus 1 over 6. Finally, we got the first one. This is the happiness in Calc2 class, right? I think I'm the only one who gets the cheering and happiness in Sequences of Series chapter. The rest is just
fun. No, you bugging, bro. I am.
1 over 9
laughing, guys.
minus 1 over 7. And then 1 over 10 minus 1 over 8, right? And then 1 over 11 minus 1 over 9.
Yo, why you just on the right list, bro?
Wow, you're just a hater. I had to repeat that so the stream catches that answer. You're just a hater. This is just serious. All right, so guys, can we cancel? Yeah, we can, right? Yeah. I have 1 over 6 and negative 1 over 6. That's dead. Let's go blue. What else can I kill? 1 over 7 and negative 1 over 7. Great. Let's go green now. 1 over 9. Oh, 1 over 8. Thank you. Yes. 1 over 8 and 1 over 8. So now you see you reach the first parenthesis that canceled completely. As soon as you get the first parenthesis that cancels completely, everything else after that will die automatically. But, you know, let's keep going. So now what else I have? Here, yellow, negative 1 over 9, positive 1 over 9. So you guys see that you are getting now second parenthesis that dies in a row. And then let's use this one. So 1 over 10. Really?
Yeah.
1 over 10, 1 over 11 will both die here. So now you see what's left over. Negative 1/4 and negative 1/5. You have 2 of them left. And this is why the answer to your question was hell no. I can make a problem that will push you to do 15 of these parentheses to leave 15 of these numbers that you have to add, or I can just leave 1 or 2 or 3. My exam, I remember it very well, when I took the exam for this, had 3. I did that problem 7,000 times because I didn't understand any of this stuff when I was learning it. So after the exam was returned and I had the telescoping problem wrong, right? Because what I did is I just kept the first number. The first parenthesis, I immediately, because the example in a class, this is the only thing that survived. One example was done. I immediately said, oh, okay, that telescoping is easy. Just pick that value. Obviously, my answer was wrong. And let's say 6 out of 10 points were gone, right? So I tried that problem over and over and over again, trying to understand what the hell happened, right? So you will understand eventually that the difference, the gap that you have between 3 and 1, right? That's the difference there. And you had the difference earlier between 1 and 0, right? So it was 1 apart. And if they're 1 apart, 1 number survives. Yeah. If they're 2 apart, 2. And then 3 for 3 and so on. So there is a pattern, right? But you discover that pattern when you do 15,000 homework examples, because it is something that you see by observation and by practicing and learning and doing. Right now, probably this piece of information is going to evaporate from your brain if you don't do any work by Monday. and then you try to do homework on Monday and you go, what the hell is happening, right?
That's when you go to math at school. What math?
You go to math.
That's 349. He says he's sick of just me going. So we need.
Is it just you every morning?
And her. And she honest time. So she literally just does it
because it's fun.
me, so I'm not home.
All right, guys, I started the back end. If you take a look at the back end, you are supposed to just take so you copy the problem in the same form and the last one, and you keep subtracting 1 as you go to populate all 6 of these. So 1 over k plus 3 becomes 1 over k plus 2, becomes 1 over k plus 1, becomes 1 over k, becomes 1 over k minus 1, becomes 1 over k minus 2. Then 1 over k plus 1 becomes 1 over k, becomes 1 over k minus 1, becomes 1 over k minus 2, becomes 1 over k minus 3, becomes 1 over k minus 4. And then we cancel everything we can. As soon as we reach, you're canceling from the back end. As soon as you reach a parenthesis that cancels both of them, everything past that will cancel towards the middle. So, can I cancel k plus 1? Yes, I can. There it is. Can I cancel k plus 3? No, I can't. Skip. Can I cancel 1 over k? Yes, I can. Can I cancel 1 over k plus 2?
Yes.
K plus 2? No. Skip. How about k minus 1? Yes. There is my first parenthesis that canceled both. Everything else will cancel by default. We can see actually that k minus 2 cancels. If I'm to write the next term, k minus 3 will die. So, there we have it. What is left? What is left is negative 1/4 minus 1 over 5 plus the limit as k goes to infinity of the 2 surviving k terms, 1 over k plus 2 plus 1 over k plus 3. Now, both of these go to 0, right? Because 1 divided by infinity is 0. So we have just negative 1/4 minus minus 1/5. The common denominator is 20. Negative 5 minus 4 is negative 9 over 20. And that's what ends the problem. Converges to negative 9 over 20 by telescoping series, TS. And that ends the lecture on 8.3. What have we done in this lecture? A quick summary. Number 1, we defined that series is a sum of a sequence, and we talked about basics of the notation. Then we talk about what it means to have a convergent series. Convergent series is the one that adds to a number, like this one adds to negative 9 over 20, like the problems before that added in geometric series to 3 over 20. So, if the series adds to a finite number, whatever that number is, first example is 4, then series converges to that number. If the series adds to infinity, because at the end you are adding infinitely many numbers and it can add to infinity, we call those divergent. The meaning of convergence and the way to calculate convergence is the sequence of partial sums in the infinite limit has to converge. So if the sequence of partial sums converges, the series converges, and you have the convergent series. Otherwise, it diverges. Then we said series can be finite, can be infinite, right? The infinite series are the ones that we're observing because finite always converge. And the fact that finite series always converge is used as a hack method here for telescoping, right? Because we go up to k. K is a finite number, right? And then we send k to infinity. So we kind of cheat. The same way we cheated for improper integrals, right? You know you can't go 0 to infinity. You go 0 to b to compute the integral, and then you send b to infinity for limit to finish off the problem. We do the same thing here for telescoping. Anyway, geometric series. You were supposed to memorize the formula for geometric series, And I said probably 15,000 times, if you don't memorize this, don't bother solving problems, because you can't make it up. You either know it or you walk. It's very simple. And I showed you how each problem is 3 seconds. You use your eyes, you look at the value for R, it follows in the first or the second condition, and the problem is solved. 3 seconds, and you're done.
Is A always going to be a constant in the geometric theory?
Yes, it's always going to be a number,
Yeah, okay.
but then this happens.
Yeah.
Where your A is your A3, obviously not, right? It's not, because A is actually 3 over 25 when you do the shifting of the counter. So I said that there will be 10 tests for series. We covered 2 today, so 8 to go. Those are next week, right? And we'll be done on Monday and Tuesday. We'll be done with those 8. So we start chapter 9 on Wednesday. And we'll be done with chapter 9 by the end of the week. Next week is, if you want the test chapter 10, 4 sections and final. That's it. 8 classes left, 7 if you're not including final. Yes?
What percentage of the final will be chapters 8, 9, 10? Or chapters 8, 9. What percent of the final is 8, 9?
Clearly a third.
A third?
That's not that bad.
I think.
What's it called? Is there going to be one question for every test on the test?
No, because you will see that these guys actually work together, so sometimes you have to get to use multiple things and combine them and so on, and some are more important than others, so some show up twice, some shows up once. Maybe I even omit one.
But this test is going to be all about series addition.
Yes, and how series is.
So wait, it's going to be chapter 8.
Chapter 9 is entry if you want it.
When do you want this exam? Thursday?
We don't think about it. Hold on.
We won't be done on Thursday.
Think about this. Think about this. If you take the percentage of the third exam, add that to the final, it would weight the hard stuff less in terms of the entire class.
Nick's a dickhead. He gonna put all 8 and 9 the hard ones. Literally. That's true. Like he's plotting,
All right.
right? When people suggest
So
that,
that's-
I see his face plotting.
We'll talk about the rest when we get. Hold on. Where are you going, guys? It's 6:30.